Hi everyone. In today's session, we'll be discussing or we'll be saying how to get the or how to represent this electric fields or electric field stress in a mathematical equation. So coming back to our basics, the potential at a point plays an important role in obtaining any information regarding the electrostatic field at that point. Potential is nothing but the voltage. The electric field intensity can be obtained from the potential by gradient operator by using the gradient or del operator. So electric field intensity is minus del dot P, which is nothing but differentiation, and the electric field intensity can be used to find the electric flux with the relation. This equation which you already seen, the electric field density is equal to D is equal to epsilon into E. The divergence of the flux density, which is again a differential or differentiating equation. Sorry. So the divergence of the flux density, which is again a differentiation, results in a volume charge density. Okay, that is del dot D is equal to rho V, or you can call volume charge density. Now, by substituting this electric field density in this flux density equation, we have del dot D, and this D is represented by epsilon into E is equal to volume charge density or rho into rho V. And again, this electric field intensity can be represented in terms of potential, and del dot, this is represented as del dot V, and this del is represented as this del on epsilon. So minus del dot epsilon dot del V is equal to rho V, or volume charge density. So this del dot del will become del square. So epsilon del square V is equal to minus rho V, or volume charge. Or simply if you can say del square V is equal to rho V, sorry, sigma V, rho V by epsilon. So this basically is our potential. So this equation is called as Poisson's equation. This equation is called as Poisson's equation. Poisson's equation. Now, this Poisson equation can be converted into a Laplace equation. How? So, for the most of the high voltage equipments, the space charge are not present, and hence this rho V can be equal to 0 or can be replaced by 0, and the Laplace equation, which is del square V is equal to rho V by epsilon, now becomes del square V is equal to 0, and this equation is popularly known as Laplace equation. Okay, and this equation, that's nothing but this. So for the high voltage engineering or for high voltage equipments, the volume charge is not present. Therefore, rho V is becoming 0, and our Poisson's equation is now getting converted into Laplace equation. If rho is equal to V, it indicates 0 volume charge density, but it allows point charges, line charges, and ring charges, and surface charge density to exist. So only this volume charge is equal to 0 for high voltage equipments, but it doesn't mean that the point charge and line charge and surface charge does not exist. So what it means is the volume charge density is equal to 0, but whereas the point charge, the line charge, the ring or surface charge density to exist at a singular location as sources of the field. And as we all know how to represent this del operator, so del operator is represented as dou by dou x of ax vector. These are the ax and ay and az are the direction vectors. So it's a three-dimensional dou by dou x, dou by dou y, and dou by dou z. We assume the increase. These are the ax, ay, and az are unit vectors with increasing in all in their respective x, y, z directions. Okay, so now the total final electric field stress is now reduced to a Laplace equation, and Laplace equation is dou square v is equal to 0, and that is nothing but dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square is equal to 0. Now this is the important point here. You can see this is a del square operator, and del is a vector. So here you can see a del dot del. So here it is a dot operation of two vectors, and with our knowledge what we know is dot operation of two vectors is a scalar quantity, and this dou square v, which is the dot operation of two vector quantities, is, as per knowledge, is a scalar quantity. Therefore this complete vector is now evaluated into a single scalar, and whenever we see about a scalar which is having only a magnitude but no direction, it becomes easy for us to evaluate, and we can go for numerical methods for calculation. Generally, this electric field stress can be for the methods for determining the potential distribution can be done by using your numerical methods or electrolytic tank method So this is when you come to numerical methods, there are some of the numerical methods which are available. Okay, so before going to the numerical methods, let us see how to estimate the electric field in some of the geometrical boundary conditions. So generally the maximum electric field EM in a given electric field configuration is important. This means the electric field over a distance d between the two conductors with a potential difference of V12 is given as electric field is equal to potential by the distance. Okay, the electric field or the maximum electric field, if you want, you can represent it by EM, is the ratio of electric potential or potential difference by the distance. This we are particularly talking about some geometrical boundary conditions. So if this is a parallel plate capacitor, this is a parallel plate capacitor separated by distance r, then the magnetic field can be represented as ratio of V by D, where V is the potential across the parallel plate capacitor, parallel plates, and R is the distance separated by this between the electrodes. Similarly, if you take a concentric cylinders with the inner cylinder radius of small r and outer radius of capital R, then this electric field or magnetic field intensity can be represented as V, which is the potential, by R, ln of R by R, natural logarithm. Similarly, two concentric cylinders that are separated by distance d, where the outer radius is separated by distance small d, and inner radius or centroid is separated by distance of capital D. You can use this. There is another term called field enhancement, which is the radio of maximum field by this. So this is not important, but this is for the general idea how the electric field or magnetic field can be represented in terms for a geometrical boundary conditions. Now coming to this numerical methods. So normally we generally the preferred method is other than numerical method we have electrostatic tank method. Okay, which we will not discuss because we will not have that as of now. But okay, I'll say about the electrostatic tank method also. The potential distribution can be calculated directly. However, there are some important rules for using this electrostatic important points which you need to remember. The equipotentials cuts the field lines at right angles. These are the important rules, and it should be understood for us when you are going for direct calculation. And when the equipotentials and the field lines are drawn to form curvilinear squares, The density of the field lines is an indication of the electric stress in a given region. In any region, the electric field is given by dV by dx, where dV is the difference voltage between the successive equipment and dx is the distance separated between the parts. That's what we have seen. Okay. So in recent methods, there are several methods or several engineers have come for solving this Laplace equations or Poisson's equation. And some of the best methods we have is finite element method, charge simulation method, and surface charge simulation method, and that which we'll be saying about calculation of this electric field stress. Okay. And one more thing, the fourth one is there, that is boundary element method, that is called as BEM. Therefore, basically there are four methods: finite element method, surface charge method, surface charge simulation method, and last, which I have not represented here, is boundary element method. We'll discuss each one of these in our coming lectures.